we are going to start multiple integrals. So we will extend our idea of definite integral, functions of 2 or 3 variables. Functions of 2 variable means f of x comma y, that is equal to, let's say, z. So you can see that here we have 2 input variables, and function of 3 variables means x comma y comma z, that is equal to, let's say, p. So here we have 3 input variables, and the output number of output variable is only 1. So that's why it is called function of 2 variable or function of 3 variable. So we already know how we can integrate function of 1 variable, or we can say function of 1 input variable or function of single variable. So for function of single variable, integrals are done over the intervals x equal to a to x equal to b. That means from x equal to a to x equal to b, f of x dx, we know the result, that is the antiderivative will be capital F x. So upper limit b, lower limit a. Now the fundamental theorem of calculus says that it will be f of b negative f of a. So same thing holds for multiple integrals, but here calculating such integrals will require some new techniques. Okay, so that will be our central focus for this session. So but the basic concepts are very similar to this type of integrals. So remember, function of one variable, that is f of x, y equal to f of x. Whenever we are integrating y equal to f of x, we need the interval x equal to a to x equal to b. But for multiple integrals, that means for function of 2 variable, we need region. That region in 2 is 2 space, and for function of 3 variable, we need region in 3 space. That means 2 dimension and 3 dimension are important. So multiple integrals can be also thought to be double integral and triple integral. So double integrals, triple integrals. In double integral, there will be 2 cases. First case is rectangular region. What will be the antiderivative over the rectangular region? And we have to evaluate double integral over non-rectangular region. For now, let's discuss about double integral. Then we will move to triple integral. So rectangular region, by this name you can easily understand that it deals with rectangle. So the region that we will have, that will be a rectangle. But non-rectangular region means here it may be a triangle, it may be a circle. We may have this type of figure where we have a parabola and a straight line. These two are intersecting. So this region is also the non-rectangular region. So these are the things I'm trying to say. That means double integrals can be evaluated over rectangular region or in non-rectangular region. So it will depend on the question pattern. Okay, so in multiple integral, whether you're finding double integral or triple integral, the main difficulty is to find the limit of integration. What will be the lower limit, what will be the upper limit? So first of all, try to understand that integration f of x dx, this is for function of single input variable, and for double integral we can extend our idea as dy dx double integral here, and the function is f of x y. For triple integral it will be f of x comma y comma z dz dy dx. So these are the chains. You can see the pattern that it is just our known integral, it is a double integral, and it is triple integral. So whenever we have this, we already know how to evaluate this type of integrals, but now the concept is coming how we can evaluate double integral and triple integral. So you can see that here we have dy dx dz dy dx. So first of all, you need to understand that dy times dx, think about x times y or y times x. So if you have a rectangle, x times y, that will give you the area of the rectangle. So similarly, x times y, that means here it is representing the area, so we can also represent this one as dA. Similarly, we can have a look on the third part, that is the triple integral. Here we have dx dy dz. Think about this type of three-dimensional figure where we have x y and z. So x y z dx dy dz, that will be the volume. So we can also represent this one as dv. So these are the notations, preliminary concepts that we need at first. So multiple integrals can be double integral or triple integral. Remember, double integral can be evaluated over rectangular region and also in non-rectangular region. You will get to know the idea if I move to some problem solving part. But before that, I am trying to discuss the critical concepts of this section. So first of all, try to understand the classification of coordinate system. So coordinate system, we can classify coordinate system into three categories. Already you know that, you are familiar with Cartesian or rectangular coordinate system. We have another coordinate system that is called cylindrical coordinate system. And the third category is spherical coordinate system. So coordinate system can be classified into three categories: Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. So you know that Cartesian or rectangular coordinate system has two classification, that is, it may be two dimension, it may be three dimension. Two dimension means you have x-axis, y-axis, and three dimension means you have x-axis, y-axis, and z-axis. Okay, so this is two-dimensional Cartesian system, three-dimensional Cartesian system. And what do you mean by cylindrical coordinate system? Suppose we have a point here, that is x comma y. So the position of this point can be directed as a vector from origin. That means this is x distance and this is y distance, then we are getting this point. So that means any point that is either in two dimension or in three dimension can be directed from origin, and we can easily find the position of that point. Similarly, here we are using Cartesian coordinate system, but let's say we have the same point p of x comma y comma z, but this point, now we are trying to locate the point not by Cartesian coordinate system, rather by cylindrical coordinate system. So let's say we have a cylinder. Based on this cylinder, we have the point here. Similarly, we have the same point p of x comma y comma z, and instead of Cartesian coordinate system, we can also use a spherical coordinate system. That means you have a sphere. So based on this sphere, you can easily locate the point where it is situated. So that is the way how we can describe coordinate system. You are already familiar with Cartesian coordinate system, but you must have to have the idea of cylindrical and spherical coordinate besides Cartesian coordinate system. So just like Cartesian coordinate system, cylindrical coordinate system can be of two categories. We can see Cartesian coordinate system is two dimension and three dimension, but cylindrical coordinate system is itself three dimension. Besides this, it has one classification, that is the two dimension, and this two dimension is called polar coordinate system. That means suppose we have the point here p of x y, that is in two dimension, x axis y axis are here. So the same point can be located by r theta. That means this is the radius or modulus from origin, the distance from origin to the point, and the angle from positive x-axis to this line, that is the theta. So instead of p of xy, we can also represent this one as p of r theta. So this is polar coordinate system. So that means polar coordinate system is a classification of cylindrical coordinate system. So the two-dimensional cylindrical coordinate system is actually called polar coordinates. And spherical coordinate system is always three-dimensional. So have you understood the coordinate system, the classification of coordinate system here? Actually, we have total three coordinate system: Cartesian coordinate system, cylindrical coordinate system, spherical coordinate system. So why we need cylindrical and spherical coordinate system? Actually, our target is to evaluate double integral or triple integral. So suppose we have a function that is in Cartesian coordinate system, that is in three-dimensional form. So sometimes it will be quite difficult to solve that type of integral. Okay, so that's why we have to look for other forms or other ways, other new techniques, so that we can easily solve the integrals. And the techniques are, let's say, we can use cylindrical coordinate system or spherical coordinate system, so that we can easily evaluate some integrals. So for some complicated integrals. So for now, we are starting from Cartesian coordinate system, and gradually you will get to know about cylindrical and spherical coordinate system. But remember, these two are very important. Cartesian in 2 dimension, Cartesian in 3 dimension. So now let's have a look on the double and triple integral. So first of all, Cartesian coordinate system, polar coordinate system, cylindrical coordinate system, and spherical coordinate system. So I can separate this one as double integral and triple integral. So in Cartesian coordinate system, double integral is generally represented by this way. That is, you have a function of two variable x, y. Here input variables are x and y. So this is f of x comma y, and we are trying to evaluate this integral. So you can see we have double integral of f of x comma y dy dx, and the triple integral, the form of triple integral will be dz dy dx, and the function will be obviously f of x comma y comma z. Here you have function for three variables. Three input variables are here, x comma y comma z. That means, let's say y equal to f of x. This is called function of single variable or function of one input variable. Input variable is one, x, and output variable is y. F of x comma y. This is called function of two input variables, or you can say now function of multivariable. So function of x comma y, and the output variable is z. X and y are the input variables. Similarly, if we have f of x comma y comma z, and let's say the result is p, that means output is p. So p is the dependent variable or output variable, but x comma y comma z are input variables. So remember, if you have a variable that is inside the parenthesis, so that variables are called the input or independent variables. Okay, so I'm just trying to discuss for this one about the forms of double and triple integral. So this is the Cartesian forms. That means double integral can be represented in this way, and triple integral will be represented in this way. So what will be the case for polar integral? You don't need polar, cylindrical, and spherical here, but you need to understand, sometimes it will be helpful for you. Whatever contents you have in week 6, that is based on Cartesian coordinate system. Okay, you don't need to go through polar, cylindrical, or spherical for now. You have another course, math 216, that is linear algebra and Fourier analysis. So in that course you will get to know all these things in details. But for now, try to understand the patterns. So polar coordinate is normally represented by r and theta. So just like dx dy, here you have dr d theta, and the function is f of r comma theta. Remember, whenever, let's say, we're transferring Cartesian coordinate system to polar coordinate system. So similarly, double integral that is in Cartesian coordinate system, if we uh, try to transfer this one to polar coordinate system, then there will be a term that is called the Jacobian. I am saying Jacobian. You can go through your BUX videos, you will understand what is Jacobian. So here we have dy dx. Whenever we are converting this one to polar, then dy dx will be replaced by r dr d theta. So this r is the extra part that is called the Jacobian. So there is a huge concept for Jacobian. For now, just try to understand that whenever we are converting double integral that is in Cartesian coordinate system and we are trying to convert this one to polar, so dy dx will be converted to r dr d theta. Okay, and here you can see triple integral. You already know that polar is two dimension. So that's why these parts are blank. Let's have a look on triple integral. So triple integral in Cartesian coordinate system is written in this way: triple integral dz dy dx, and the function is f of x comma y comma z. If we want to transfer this one to cylindrical coordinate, then it will be triple integral. The function will be f of r comma theta comma z. Dz dy dx will be obviously dr d theta dz, just like polar coordinate system. But remember, there will be one extra part, that is r. It is called as Jacobian. So dz dy dx will be converted to r dr d theta dz. Similarly, if we try to transform this triple integral that is in Cartesian coordinate system to spherical coordinate system, then we need this one, that is f of, in spherical coordinate system, the point is denoted as rho theta phi. In cylindrical coordinate system, the point is denoted as r theta z. In polar coordinate system, the point is represented as r theta. And you know that in Cartesian coordinate system, if you have two dimension, then x comma y is the representation for a point, and similarly x comma y comma z is the representation for a point that is in three dimension. So since you have spherical coordinate system here, so rho theta phi, so it will be rho theta and phi, or you can say phi. So f of rho theta phi with d rho d theta d phi. But since we are transferring Cartesian triple integral to spherical triple integral, there will be a Jacobian that will be here, rho square sine phi. Let me write again correctly. It will be rho squared sine phi. So dr d theta dz or dz dy dx will be replaced by rho squared sine phi d rho d theta d phi. You can have a look on calculus written by Anton Bevins Davis. So you will get all the ideas in chapter 14, that is multiple integral, double integral, double integral in non-rectangular region, you can see. Then double integrals in polar coordinates. You can see triple integral is in section 14.5. Then triple integrals in cylindrical and spherical coordinates. You will get to know this one in section 14.6. And finally, there is a term that is called chains of variables in multiple integrals, or we can say Jacobians. So this thing is very important whenever we are trying to convert double integral or triple integral that is in Cartesian coordinate system to spherical coordinate system, then we need Jacobian. Okay, so for now I have directly written the Jacobian R for polar coordinate, R for cylindrical coordinate, and rho square sine phi for spherical coordinate. Whenever uh, you will study about Jacobian, you will get to know how we can evaluate R or rho square sine phi. Okay, so for now, today we will discuss about double and triple integral. So let's start. So these are the pre-concepts, preliminary concepts that we have to know before starting multiple integral. So first of all, let's start with double integral. So double integral in Cartesian coordinate system. F of x comma y is the function. This is the continuous function over y equal to c, y equal to d, x equal to a, x equal to b. That means you have now a region. The region is represented as R. So try to understand the difference between this one. F of x dx from x equal to a to x equal to b. Here we have the interval. X equal to a is the vertical line. X equal to b is another vertical line. And inside this interval, the function f of x is continuous. That means for this type of integrals, we need intervals. But here we have region. You can see if I take the help of Cartesian coordinate system in 2 dimension, so x equal to a, that is obviously vertical lines. From the concept of geometry, you know that x equal to a is vertical line. This is going with this one. X equal to b is another vertical line. Y equal to c, that will be the horizontal line. This is y equal to b. Y equal to c, sorry, y equal to c, that is a horizontal line. I have written b again, so it will be c, let's say. So y equal to c is the horizontal line, this one. Y equal to d, that is another horizontal line. So now you can see that the intersecting part of x equal to a, x equal to b, y equal to c, y equal to d, this is the region R. Under this region, we have to evaluate this integral. You have the function that is acting as the height, x, y, let's say z, x, y, z. That means this will give you the volume of a three-dimensional shape. Do you understand my point? Try to respond. You have x, y times z. So that will give you the volume. So here comes another concept, that by using double integral, we can find the area and volume. So how we can find the area? So if we have double integral of f of x comma y dy dx, you can see x times y times f of x comma y. Let's say f of x comma y as z. So x times y times z, that will give you actually the volume. But if you have a double integral, with only dy dx, and the function f of x comma y is just 1. That means you have just x times y. So x times y is actually giving you area. You know that x times y, that will give you the area of any rectangle. So that is the thing. Remember, the formula is, if you have double integral dy dx with with a function 1, then it will give you the area. So this is in Cartesian coordinate system. Do you understand my point?
Yes, sir.
Similarly, let's say we have triple integral. So try to understand that if we have a triple integral, so triple integral in Cartesian coordinate system, I am not describing for now cylindrical and spherical. So triple integral will be, let's say, f of x comma y comma z dz dy dx, and you have a function f of x comma y comma z as 1, and you have dz dy dx. So you can think about like this, that x times y times z, and you have 1, that means you have the same thing, x times y times z. What you will get? Area or volume? You will get volume, x times y times z, and you have the function 1. So this will give you the volume. But if you have x times y times z times some other function, so it will actually give you a four-dimensional shape. Do you understand my point?
Yes, sir.
Okay.
Yes,
So
sir.
x times y times z, that means it is the three-dimensional figure. That means for three-dimensional figure, you will get the volume of a cube, volume of a sphere, like that. But if you have x times y times z, that means dx, dy, dz with f of x comma y comma z, let's say it is x squared y z, this is the function with dz, dy, dx, then it will not give you the volume. Remember, it will be one four-dimensional phenomena. It may be mass. You know that from the concept of physics, you know that rho equal to m by v. That means density equal to mass over volume. So m equal to rho times v. So you can see dz, dy, dx, that is actually dv. So with a function, let's say this is rho. So rho times v, that will be actually mass. So do you understand my point? That
Yes,
means
sir.
that means you have the triple integral, and rho is acting as this function f of x comma y comma z, that is acting as the density function, and you have the volume v dv. Instead of dv, we can write dz dy dz dx, dz dy dx. So you will get the mass of a shape. Okay, so that means, remember, if you have dz dy dx with 1, then it will give you volume, and if you have dz dy dx with f of x comma y comma z, so that will be not confined in three dimension. It will be another new phenomena. It may be mass, or it may be some other things, maybe center of gravity, like that. So these are the things. That means these are the applied part of double and triple integral or multiple integrals. So for now we are discussing about double integrals. So remember, if you have the function 1 with dy dx, then it will give you the area. And if you have f of x comma y dy dx x y z, so it will give you the volume. So you can see, if you have x equal to a, x equal to b, y equal to c, y equal to d, both are constant values or real numbers, then it will be obviously a rectangle. This is x equal to a, x equal to b, y equal to c, y equal to d. So obviously you will get a rectangular region. So at the very beginning of this session, I have told you that double integral has two classification. We can evaluate double integral in rectangular region or in non-rectangular region. Rectangular region means you have a rectangle. Non-rectangular region means you may have a circle, you may have a parabola, or you have this type of shapes, or you will have this type of triangle. So that means these are not rectangles. These are the things. So double integrals can be evaluated over rectangular region and in non-rectangular region. So remember, whenever you have, how can you recognize whether you are provided with rectangular region or non-rectangular region? In rectangular region, you will have the constant values, that means x with inequality a to b, y with c to d. That means lower limit of x is a, upper limit of x is b. Lower limit of y is c, upper limit of y is d. That means this a, b, c, d are real numbers. So by this you will understand that this is rectangular region. But non-rectangular regions are, that means instead of constant values, you will have a function. So that is non-rectangular region. So this is called double integral. That means double integral form is this one. So let me discuss again. So we have a theorem. The theorem is called Fubini's theorem. This theorem is very important. Fubini's theorem. Fubini was an Italian mathematician. His full name was Guido Fubini. Okay, so based on his name, it is now known as Fubini's theorem. So the theorem says that if you have a region, if you have a region, rectangular region, and the rectangular region is defined by the inequalities a less than x less than equal to x less than equal to b, and c less than equal to y less than equal to d. That means the lower limit of x is a, upper limit of x is b, lower limit of y is c, upper limit of y is d. This a, b, c, d are constant values, real numbers. Then what we can expect, if we have a function f of x comma y that is a continuous function, if f of x comma y is a continuous function, if we have a continuous function on this rectangle, that means x equal to a, x equal to b, y equal to c, y equal to d, under this rectangle or on this rectangle the function is continuous, then the double integral f of x comma y dy dx, that is from, you have to understand that this part, you can see at first we have dy. So for the second integral, the limits will be for y, it will be y equal to c, y equal to d, and finally we have dx. So the first integral will be x equal to a, x equal to b. So this is actually giving us the volume x, y, z. So that means it is giving us the volume. So Fubini says that, mathematician Fubini says that if you have a rectangular region, then we can change the order. That means instead of dy dx, we will get the same result if we take dx dy. So this time x comes first. So here x equal to a, x equal to b, y equal to c, y equal to d, and the function is f of x comma y. So this is how we can evaluate double integral f of x comma y dA. dA means dy dx dy, anything. So over a region or rectangle R. So this is how we can describe Frobenius theorem. So Frobenius theorem describes that we can, if we have a rectangle, then we can replace the order. At first we can integrate in terms of y, then x, or we can integrate in terms of x, then y. Do you understand my point? Do you get the idea of Frobenius theorem?
Yes, sir.
Thank you. So the same thing holds for three dimension. Let me describe the same thing again. You have, instead of r, if you have now, instead of rectangle, let's say you have a cube, where that means, let's say G is a rectangular cube or box, let's say box, rectangular box, that is defined in the intervals a less than x less than equal to b, c less than equal to y less than equal to d, and let's say k less than equal to z less than equal to l. Then if we have a function f of x comma y comma z, since it is three dimension, so f of x comma y comma z is continuous, same thing is here, continuous over or on G. Then triple integral of f of x comma y comma z, let's say if we maintain the order at first dz dy dx. So here we have f of x comma y comma z dz dy dx. Since dz comes first, so that means this integral, the third integral, will be for z. So z equal to, lower limit of z is k, z equal to k, z equal to l, upper limit. Then y, so y equal to c, y equal to d. Then x equal to a, x equal to b. So this is how we can evaluate triple integral. But since we have rectangular box and all the limits, that means x limit, y limit, and z limit are constant, real number, so what we can do, we can also change the order based on our convenient position. That means we can use dx then dz then dy, or we can write whatever we want, let's say dy then dz then dx. So do you understand my point? Here the function is same, f of x comma y comma z. So if I write dy at first, then this limit will be for y, for z it will be z, and finally for x, here the limit will be for x. So this is the Frobenius theorem in two dimension and three dimension. That means we can replace the order if we have constant limits. That means if we have rectangle that is in two dimension, or if we have rectangular box in three dimension, then we can replace the order. Okay, so let's move to some problem solving part. You will understand what we are going to do. So let's take some examples from double integral. Okay, let me think about a problem. Okay, let's say we have to evaluate x plus 3 dy dx, and we have the limits of integration 0 to 2, 0 to 1. So our target is to evaluate this integral. This is actually a double integral. So evaluate the double integral, this one. So you can see that it is going with f of x comma y, although here it is y free, but actually it is x comma y form. So f of x comma y dy dx. So this function is f of x comma y. So it is, let's say this is length, width and height. So this is actually giving us the volume of a three-dimensional shape. So first of all, the same problem can be uh, represented in alternative way. Let's say instead of this one, you have the double integral x plus 3 dy dx. Here you have the region or rectangle R, and R is defined as 0 less than x less than 1 and 0 less than y less than 2. This is the alternative question. Try to understand this one also, because the question is looking different. Both questions are looking different, but actually the solving technique is same. Here the limits are already here, but in this part you have a region, and the region is defined later. X limits will be 0 to 1 and y limits will be 0 to 2. So you can see, first of all, tell me 0 to 2, if we have this one, so is the limits for y or x 0 to 2?
Sir, y.
Y. Obviously y, thank you. It will be y equal to 0, y equal to 2. And for x, x equal to 0, x equal to 1. So okay, so if we have to evaluate this double integral, what we can do, we can integrate partially. So that's why it is called partial integral also. Okay, multiple integrals are also called partial integration. So first of all, our target will be, okay, first of all, I want to highlight that since we have constant values x equal to 0, x equal to 1, y equal to 0, y equal to 2, let's draw the figure, because sometimes in your question there will be some requirement. Is guess the region R. Okay, so that's why you have to also know how we can draw the region. So here you can see x equal to 0 and x equal to 1 is given. So in Cartesian coordinate system, x equal to 0 will be this line, and x equal to 1, let's say this is x equal to 1. Y equal to 0 is actually the x-axis, this is the horizontal line, and y equal to 2, this is 1 2, so this is y equal to 2. So you can see that the region that we have found by these four vertical for, that means two vertical lines and two horizontal lines, the intersecting parts are becoming this. So this is our region. Under this region we are not drawing the three-dimensional shape. The three-dimensional shape is the height. You will understand if I move to this one. So we have the function, that means at first limits are x equal to 0. So you can see this is x equal to 0, x equal to 1, this is another limit, upper limit, y equal to 0, that is the horizontal line, and we have y equal to 2. So y equal to 2. So finally, we have found the intersecting part. You can see, can you see this portion, this one in two dimension? Here we have the region, this one. Do you understand?
Yes, sir.
Yeah, that's why I have drawn the same figure. We are viewing the rectangle from the top position. Okay, So this is the top view. We are not drawing the three-dimensional shape. So that's why our target, our focus will be on the two-dimensional shape only. What is the region? If the region is rectangle, we can easily integrate. We can also rewrite the order at first dx or dy. So let's try to integrate this one. Here you have, at first, once we have mentioned x equal to 0, x equal to 1, y equal to 0, y equal to 2, so we can then skip this. We can just write 0 to 1. At first, let's integrate for y. Whenever we are integrating for y, then x will be constant. Remember, x will be constant. And whenever you are going to integrate in terms of x, then y will be constant. That's why this is called partial integration. It is just like partial differentiation. So it is called partial integration. So first of all, integration from 0 to 1. Since x plus 3, we are integrating in terms of y. So x plus 3 is constant. So x plus 3 can be pulled out. We have 0 to 2 dy. And finally dx. So actually dy with 1. Okay. So now what we can write? Integration from 0 to 1, x plus 3. So what will be the integration? Integration of 1 in terms of y, it is actually y. So now we can apply the fundamental theorem of calculus, that is antiderivative at upper limit, antiderivative at lower limit. So integration from 0 to 1, x plus 3. So here we have y. We can apply the fundamental theorem of calculus, upper limit, negative, lower limit. Do you understand my point?
Yes, sir.
Yes, sir.
Okay, so finally 2 minus 0 is actually giving us 2. So here we have 2x plus 3 dx. So since 2 is constant, now we can pull out 2 before the integral. We have x plus 3 dx. So here you can see double integral has been converted to our non-integral. We have only one integration, that is one integral sign. So we can easily solve this one. So let's solve this one. X, integration of x is x squared by 2. Integration of 3 is 3x. Upper limit 1, lower limit 0. Again, we can apply the fundamental theorem of calculus. Fundamental theorem of calculus means I am describing about this one. Integration from a to b f of x dx. If we have the antiderivative f of x, then upper limit b, lower limit a. So fundamental theorem of calculus says that antiderivative at upper limit, negative antiderivative at lower limit. So here we have already the antiderivative, x squared by 2 plus 3x. So here we need to input upper limit at first, then lower limit. So what we can do? We can input upper limit at first. So 2, 1. That means at first let's work with 1. So 1 is squared by 2 plus 3 times 1, that is 3. And if we input 0, it will be 0 plus 0. Okay. So finally we're getting 1 plus 6. So that means we have 7. Do you understand my point? The result is already found. So 7. So the physical phenomena will be the integral is actually giving us the value of volume of a three-dimensional shape. So we have found 7. So that means it's actually the volume, and volume is meter squared, sorry, meter cube, centimeter cube. So we can write unit cube. You don't need to write all these things, but for applied part, these notations are used. Okay, So have you got the idea?
Yes, sir.
Okay, so let's solve another problem from double integral. Then we will move to non-rectangular region. Let's say we have a rectangular region from 2 to 4, from 0 to 1, x squared y dx dy. You can see this time instead of dy dx we have dx dy. So first of all, try to understand the limit. The limit that we have here 0 1, it is for x or y. This is for x because x comes first. Have you understood?
Yes,
Then
sir. Yes.
y. So y is 2 and 4. And this is the function f of x comma y. So we can draw the region because sometimes in your question there will be some requirement that is just the region only. You don't need to draw the three-dimensional figure, just draw the region. So here we have x equal to 0. X equal to 0 means this line y-axis, and x equal to 1, this line, this is a vertical line. Y equal to 2 1 2, so this is y equal to 2, and y equal to 4 3 4, so this is y equal to 4. So actually we have the bounded region. This is x equal to 0 and x equal to 1. We have this region. This is looking as a rectangle. You can see this is a rectangle. So that's why we can easily understand whenever we will have constant values in the limits, then obviously it will be a rectangle. So in this part we can easily integrate. Okay, so or we can understand by another way because this concept is important. Suppose we don't have the limits. Try to understand this part is very important whenever we will move to non-rectangular region. So we have this integral, and based on this figure you have been provided a figure. Okay, so based on this figure you have to find, okay, so based on this figure you have to understand what will be the limits. Okay, suppose all these things are not here. Suppose it is 2, this is 4, this is 0, this is 1, and all the informations are not here. So based on this figure your region is this. Based on this figure you have to understand what will be the limit. Okay, I'm constructing the problem now. So first of all, x squared y dx dy. So now we have to think about the x limit. So for x limit, always try to understand that we have to look from this way. This is the in, this is the out. In of x, out of x. So for x limit, you have to look horizontally, and for y limit you have to look vertically. In of y, out of y. So okay, first of all let's try to understand what will be the limit for x. So in of x, what line is coming at first? This line is coming, this vertical line is coming. Yeah,
Yes, sir.
so do you understand what is the equation of this line? This is x equal to 0.
Yes, sir.
So this is the inside, that means in of x. That means the lower limit is x equal to 0. Upper limit of x, It is
with
coming.
1.
So it is x equal to 1. Based on this one, you can understand this line is x equal to 1. So x limit is done. Now, what will be the y limit? So
2, 4.
y equal to 2, y equal to 2 will be the lower limit. So you have to look vertically, vertically in, vertically out. So vertically out, you are getting y equal to 4. So y equal to 4 is the upper limit. So finally, now we have the complete problem. Is that okay?
Yes, sir.
So sometimes your limits will be given, or sometimes you have to understand what will be the limit based on the figure or based on the information that will be provided in your question. Okay, so let's try to solve this one. Same thing, whatever concept I have written here, in of x out of x, in of y out of y, same thing will be very helpful in non-rectangular region. After this, I will uh, discuss one or two problem from non-rectangular region. So okay, let's integrate at first. So already we have mentioned y and x, so we don't need to mention again. So let's integrate first for x. So we have 0 to 1. I am using this square bracket so that you can easily separate what we have to do at first. Okay, so this integral is written in this way. Now you can see that we are integrating in terms of x. So obviously y will be constant. So that means what we can do, we can pull out y before this integral, not here. We are writing here. So y is constant, that's why we have pulled out. So x squared dx dy. And then we are getting integration from 2 to 4 y. So integration of x squared, that will be x cube over 3. Upper limit of this integration is 1, lower limit is 0. And we have dy. So integration from 2 to 4 y. So let's apply fundamental theorem of calculus for the first integral. Here we have x. So if we input 1, so 1 cube by 3, it will be 1 by 3. And if we input 0, 0 by 3 will be 0. So finally, we are getting this. So let's try to solve this from this part. From here, we are getting integration from 2 to 4 y 1 by 3 dy. Now, this double integral has been converted to single integral. So again, we have to integrate, but this time for y. So 1 by 3 is constant. So we can pull out here. So now let's try to solve this. So integration of y is y squared by 2. I hope already you have control over the basic skills of integration. So I am using the power rule. Now the fundamental theorem of calculus will be used. Here you have y. So where you have y, input upper limit, then lower limit. So one,
স্যার আমার একটা
yeah,
কোশ্চেন ছিল
yeah,
স্যার।
sure.
স্যার ওই যে এক্স কিউব বাই 3 যখন হয়েছিল তখনই যদি 1/3টা আউট মানে ব্র্যাকেট থেকে বের করে নিই তাহলে কি মানে যে এক্স কিউব
No
বাই
problem, no problem. Yeah, we can easily pull out this 1 by 3 before.
তারপর
Yeah,
শুধু এক্স কিউবের উপর লিমিটগুলো
yeah.
বসালে হবে?
Then at that moment that will be for only for x cube. You have to work with x cube only. 1 cube
ওকে স্যার,
minus 0 cube, no problem. Okay,
ওকে ওকে স্যার,
that will be more convenient.
ওকে স্যার।
Okay, so finally now let's input upper limit. Okay, let's do the same thing here. Whatever you have told me, you can see we have 1 by 2. So let's bring out 1 by 2 before.
Yes,
Then we have y squared upper
16 minus 4.
2. Do you want to tell about this one?
Yes, sir,
This
16 minus 4.
Yeah, so that is we have
Half money total.
16 minus 4. That means 4 is squared, negative 2 is squared. So that means 1 by 6 times 12.
Yes, answer will be 2.
2. So
Yes.
now let's try to understand what the problem says. If it is a real life phenomena, then it will be x times y times z, that will become volume. So we can think about that the result that we have found, that is actually unit cube. But you know, don't need to write unit cube. But for your better understanding, I am writing unit cube.
Okay,
Because
sir.
actually everything that we are discussing in calculus,
Is
different
unit.
calculus deals with rate of change, and integral calculus deals with area, volume of any kind of shape, area, volume, length, surface area. Okay, so these are the things for double integral in rectangular region. Remember, if we have constant limits, then it will be rectangle, but things will not be convenient always. So let's start double integral in non-rectangular region. So double integral in non-rectangular region. Let's discuss directly from a problem. We can take one problem from our reference book, or let me construct one. Let's say we have mm, we have a simple function x squared, and the region is given as R with, let's say, dA. So here we have to evaluate this integral where R is the region bounded by let's say y equal to 16 over x, y equal to x, and x equal to 8. So we have this integral at this moment, but the limits are not here. And the region that we have R, that are not constant values. X equal to 8, that is a constant. But y equal to x, this is a function. Y equal to 16 by x, this is another function. So y limits are not constant. Do you understand?
Yes, sir.
So if we don't have constant limits, then we can easily understand that the region that we will have R, that will not be a rectangle. It will be some other curves. So Fubini's theorem will not be applied directly. That means we can't change the order. That means if we have dy dx by using Fubini's theorem and if we have the rectangular region, then we can easily change the order dx dy. So this thing is not allowed if we have non-rectangular region. At first, we have to integrate for the function part, and then we have to integrate for the constant limits. So now the main difficulty is to understand the limit. So for this, you have to draw all the figures that you have here. Similarly, whatever we have done here, that means, let's say we have x equal to 0, x equal to 1, y equal to 0, y equal to 2. So at first we have drawn all the vertical lines and horizontal lines, then we can go through the calculation. Similarly, we will do the same thing. Here we have three functions.
Yes, sir.
Okay, so
Sir,
what?
y will be 8 and 2.
Yeah,
Y will be 8 and 2. I mean,
8
2.
and 2. Okay, let's at first draw the figure. Then you will understand.
Okay, sir.
If you understand this concept, then Whatever problem you will get in double integral, it will be easy for you. So y equal to 16 over x, and we have y equal to x, and we have x equal to it. So let's try to draw the figure. How we can draw? Let's try to understand by using tabular form. Here x is input, y is output. If we input 0, the function will be infinity, undefined. So let's start with, let's say 1. If we input 1, we will get 16. If we input, let's say 4, we can choose any random value. If we input 4, we will get 16 by 4, that means 4. If we take 8, 16 by 8, that will be 2. That means the points are 1, 16, 4, 4, 8, 2. Similarly, we can draw this y equal to x, x, y. We can start from 0. If we input 0, it will be 0. If we input 1, it will be 1. We can input 4, then it will be 4. It will be, we can input 8, it will be 8. So this is how we can find some points.
Yes, sir.
So let's try to draw the figure. So here we have the Cartesian coordinate system. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. Okay. Here we have 1, 2, 3, 4, 5, 6, 7, 8. So at first 116 point is here, then 4, 4. I am drawing this curve, y equal to 16 by x. So 1, 4, this point. Then 4, 4. 1, 2, 3, 4. 1, 2, 3, 4. The point location is here. 8, 2. 8 and 2. Can you understand the location?
Yes, sir.
So the curve that we will find by joining these 3 points will be this one. This is y equal to 16 by x. Okay? Up to
Yes, sir.
now, any problem?
No,
We
sir.
have this figure. Now let's draw y equal to x. So here we have 0, 0 point, 1, 1 point, 4, 4 point, and 8, 8 point. So 0, 0 point is here. This is 0, 0 point.
Yes, sir.
1, 1 point will be here. 4, 4, this point. 8, 8, this one. So that means we can join this point, and the graph of y equal to x is this. So
Yes,
this is y equal to x. And
yes.
now we have another curve. Don't forget that we have 3 curves. This
X
one,
equal to
x equal to 8. So x equal to 8 is a vertical line. Whatever curves you will have in your region R, you have to draw all the figures, or you have to understand the limit from these figures. So now, whatever region we have by intersecting all these curves, y equal to x, y equal to 16 by x, x equal to 8, you can see we have found this region, right?
yes, sir.
By y equal to x, by y equal to 16 by x, and x equal to 8. This is our region. So do you understand my point?
Yes, sir. The source.
So invisibly, you can see that here we have a point. So we can think about a vertical line here, because this is our boundary. From this part to this part, we have a region. So what will be the point here? Or the equation of this line? This point is 4, 4. That means this is x equal to 4, right?
Yes, sir.
Okay. So this is x equal to 4. Now, let's start our calculation. Our integral is this.
Yes,
So we have this integral. Now we are targeting for the limits. Without limit, we can evaluate the integral. So x squared, instead of dA. We can also write dy dx or dx dy, but for now I am writing dA. So first of all, try to understand x limit. So for x limit, in which way we have to look, horizontally or vertically?
Sir, x. Sir,
For x, you can have a look here. For x, we have to look
for
horizontally, in x, out
horizontal.
x. For y,
Yes.
vertically, in y, out y, right?
Yes. Yes, sir.
Okay. So we have this region. If I draw again, if I just pick up this part, this is x equal to 4, this is x equal to 8, and we have this region, y equal to x, y equal to 16 by x. So first of all, think about x limit in x. What is the in part? X equal
4.
to 4. So if we take, that means let's figure out limit of x. So limit of x will be 4, that is the lower limit, and upper limit will be out of x is x equal to 8. So 4 to 8, right?
Yes.
And limit of y. For limit of y, we have to look from bottom to top. That means vertically downward to upward. So at first, which curve is coming? Y equal to this one.
S-
Y equal to
Yes,
16.
sir. 16 by.
So
Yes.
for y limit, 16 by x will be the lower limit, and upper limit will be y equal to x, right?
Yes.
So finally done. But here there is a restriction in Frobenius theorem that since we have now non-rectangular region, it is not a rectangle. The region that we have found, is this a rectangle? No, this is not a rectangle. This is another shape. So,
Yes.
so at first we have to integrate in terms of y, because y limits are function 16 by x and x. So at first we have to integrate in terms of y. Do you understand my point?
Yes, sir. So,
So now we can write, any problem here? At first, we will integrate in terms of y, then x. So y limits, let's now write the y limit. Y limit is y equal to 16 by 8, lower limit, and y equal to x is the upper limit. For x equal to 4 is the lower limit, x equal to 8 is the upper limit. Do you
yes.
understand my point?
Yes, sir.
So this is how we can go forward. Now the problem is, okay, but sometimes in your question, you will be provided with this information, then you don't need to have any tension with the limits. But if you have this type of questions, this one
Sir, এটা
you
মনে
just get, yeah.
Yes, এটা ফাইনাল আসবে মনে হয়। মানে
It depends, but I am trying to make you understand about the concept, okay?
yes,
My
sir.
question pattern will be different. Your question may be in this form or in this form. If it comes with this form, this one, then you are lucky. But if you have this one,
Sir,
then
I
you
am never lucky, sir. আমার
then
ওইটাই বড়
you have to first draw the curves and then you will find the limits. Okay. Without wasting time, let's try to evaluate the integral. So at first, you can understand that since y limits are function 16 by x 6 or x, these are not constant values. You can understand these are not constant values, so we have to integrate at first y, not x. We can't change the order. We can write dx dy here. This is the restriction.
Yes,
So integration from 4 to 8, at first let's integrate in terms of y. So here you have x squared is we are integrating in terms of y. Let me
x স্কয়ারটা বাইরে চলে
yeah, let me separate here, then you will understand. So x squared is written before, so now we have integration from 16 by x to x 1 dy in terms of x. So integration from 4 to 8 x squared. So integration of 1 in terms of y, it is obviously y.
y
upper limit x, lower limit 16 by x, and we have dx here. So this is called partial integration, 4 to 8 x squared. So at first let's input upper limit. Upper limit will be replaced where we have a y. So x, then there is a negative that is coming from fundamental theorem of calculus, f of b negative f of a. So now input the lower limit, 16 by x. So now we can see that whatever complicated integral we have previously, it is coming
Solved.
as simple as possible. So now we can write it is x cube negative x squared and 16 by x. It will be 16,
16.
right?
Yes.
So now we can write uh, integration of x cube, that is x to the power 4 over 4 negative 16 x squared by 2. Upper limit 8, lower limit 4. Again, fundamental theorem of calculus will be applied where we have x. Definitely, we need to input upper limit and then lower limit. So at first, let's work with upper limit. Okay, here we can also simplify 2 and 16. The result will be 8. So we are getting actually 8 x squared here. So that means at first we can input upper limit 8, 8. So upper limit is done. Let's work with lower limit. So input lower limit here. Lower limit is 4. So now it is up to you. You can easily find the result. Is that okay?
Yes, sir.
Okay. So I will take another 10-minute times so that you can understand another problem, similar problem. Okay.
Okay, sir.
So by this problem, I will end up the session. Let's say this time we have to evaluate. Let me think about a problem. Evaluate a double integral x y squared dA, and we have a region where R is defined by y equal to 1, y equal to 2, let's say x equal to 0, and we have y equal to x. So this is the integral, double integral, and we have the limits. So you can easily see that this time y limits are constant, but x equal to 0, and here we have x equal to y or y equal to x. In some parts, that means for all the 4 parts, we don't have constant values. We have constant here, here, and here, but this is a variable. So it will not be a rectangle. The region we will have, that will not be a rectangle. Okay. So
Yes, sir.
just to understand the limits, what we can do, we can draw the figure at first. So here we have y equal to 1. Let's say 1 here and 2. This is 1, this is 2, and this is 0, 1, 2, 1, 2. So we have to draw all the curves. Let's draw y equal to 1. So y equal to 1, from the concept of geometry, you know that y equal to 1 is the horizontal line that is going with this.
Direction.
Yeah. It is parallel to x-axis. Y equal to 2 will be again a horizontal line here. This is y equal to 2, and this is y equal to 1. Is that okay?
Yes, sir.
X equal to 0. X equal to 0 is this line. So
Yes.
this is x equal to 0. Can you please mute your mic? So x equal to 0 and y equal to x. So Already we have drawn y equal to x in our previous problem. Y equal to x is looking like this curve. This is the straight line. So that means for you have a problem. If you have a problem, you can also draw by this way. At first, you can input x, then you will get y. If we input 0, you will get 0 here. If
Yes,
we input x as 1, you will get 1. If we input x as 2, you will get y as 2. So 0, 0 is the point, 1, 1 as the point, 2, 2, this is another point. So this is actually a straight line
yes,
equal to x. So y equal to x. Finally, everything is done. So based on these four curves, x equal to 0, y equal to 1, y equal to x, y equal to 2, what is our bounded region? Can you understand? This is our bounded region, right?
yes, sir.
So
Yes, sir.
let me write clearly. Let me draw again clearly here. We have this shape finally. This curve is giving us the information that it is y equal to 1, it is y equal to 2, it is x equal to 0, and this is y equal to x. So now our target is to understand the limit. So x y squared dA. So what will be the limit of x at first? For limit of x, we need to have a look in this direction. In of x, out of x. Is that okay? So
Yes,
at
sir.
x equal to 0 is coming, right?
Yes, sir.
This is the in part. At first, this line is touching this curve, and then this line is touching this curve. So finally, y equal to x. Our target is to find x limit. So actually, we have here alternatively x equal to y, right?
Yes, sir.
So that means apparently it is looking y equal to x, but actually we have x equal to y. So x limit is 0 to y. Let's figure out y limit. For y limit, can you,
1 to 2.
in which direction we have to check?
So low to bottom to top.
Upper. Okay,
Yes,
that is from
bottom.
bottom to upward, bottom to top. So at first, if we think this is a line that is going through this part, so at first it is touching this line. So it is y equal to 1. And then this direction, in this direction, we will get y equal to 2. So this is the way how we can find y limit in of y, out of y. So that means 1 to 2. Is that okay?
Okay, sir.
So now we can write this one as, at first let's say it is x equal to 0, x equal to y. X limit is 0 and y limit is 1 and 2. So you can understand that this time it is not a rectangle, and
Yes, sir.
what you can write instead of dA, we can here we can replace it by, let's say, dy dx. But I have written in this form. Can we solve this one by this way? Whatever representation we have now, can we solve this one?
Sir, extra. Yes,
Yeah,
sir. We can solve.
it is
Sir,
not possible. At first, you have to work for the function part, variable part. Then finally, you have to move for
what?
constant part. So we can write by this way. Since y limits are constant, so we will work for y later.
Okay, sir.
So we can rewrite this one as x equal to 0, x equal to y, x y squared, then dx dy. If you write this one previously, no problem. Same meaning is this one and this one. The two equations are representing the same meaning. Okay. So, but the problem is you have to rewrite this one because x limits are function. X equal to 0, this is constant, but x equal to y, this is a function. So you have to work for x at first. Do
Okay,
you
sir.
understand my point?
Yes, sir.
Okay, so now it is easy. So let me separate so that you can easily understand which part should be integrated at first. So we are going to integrate in terms of x. So at first we are integrating in terms of x, so y will be constant. Y equal to 1, y equal to 2, y squared is pulled out. So we are integrating in terms of x, x equal to 0, x equal to y, and we have x. Xy squared, xy squared, and that is here. So, and we have dy. Let me separate again so that you can understand clearly. So, okay, at first let's integrate in terms of x. So now we can write 1 to 2. Need to write y again, y equal to 1, y equal to 2. We can skip. Okay. Integration of x squared by 2. Upper limit y and lower limit is 0. Do you understand? Upper limit of x is y
Y.
and lower limit of x is 0.
0.
Is it okay?
Yes, sir.
Don't do a mistake here. That means you are writing x here. No,
No, sir.
this is y and 0.
0.
2 and 1. These are the limits. So upper limit, lower limit.
Okay, sir.
So okay, this is dy,
Yes, sir.
and finally 1 by 2 is constant. Let's bring 1 by 2 for our betterment. So we have x squared y 0 dy. So 1 by 2. Now we can apply the fundamental theorem of calculus. Integration from 1 to 2 y squared. If we apply the fundamental theorem of calculus, at first we need to locate this. So where we have x, input y. So y is squared. Negative 0 is squared. That means 0. So we have dy. Okay.
Okay, sir.
So from this, if I solve this one, 1 by 2, uh, then we have integration from 1 to 2, y squared and y squared dy. So actually we have integration
Y
from
to the power 4.
y to the power 4 dy. Thank you. So 1 by 2, integration of y power 4, it will be y power 5 over 5. Upper limit 2, lower limit 1. So again, for our simplicity, we can bring 1 by 5 before so that the antiderivative looks simple and we can easily calculate. So upper limit is 2, lower limit 1. Be careful, we have to input upper limit where we have y, lower limit where we have y. So if we do this, that means we are getting 1 by 10, then 2 power 5, negative 1 power 5. 1 by 10, it is 32, negative 1. So we are getting 31 over 10. That means 3.1 is the result.
Okay,
Do you
sir.
understand my point?
Yes, sir.
So this is the thing that you have in double integral. You will always have a problem in finding limits, but whatever concept I have described here, you have to look in this way for x limits, in this way for y limits. Okay, for x limits, look horizontally from left to right. For y limits, look vertically from bottom to top. Is that okay, my dear?
Yeah. Yes, sir. Sir.
So thank you for joining the session. If you allow me, I can conclude the session here.
Yes, sir.
And hopefully we will see again in next consultations. Okay.
Okay, sir. Thank you.